Hello again. Tonight we're going to talk about extrastellar CME observations. So, extrastellar means it's from stars that are not our sun, stars in other solar systems within the Milky Way. CMEs are coronal mass ejections. When the magnetic field lines of a star get entangled, twist around, and then snap back, when they snap back, they release large amounts of plasma, ionized hot gas, but also subatomic particles. They also release a lot of light, electromagnetic radiation, and they release it out into space at very high velocities, at about 5.37 million miles per hour. Nowhere near the speed of light, but fast. And they release high quantities of that in small discharge, small size discharge, small, bigger than the Earth, but small as far as the total size of a star. Anything nearby to them, when that CME strikes, let's say, a planet or a moon, is going to strip away any atmosphere. But we're not close enough to our sun for that to have an effect. What it will do is affect satellite communications, maybe push some satellites downward. Our electromagnetic shield of the Earth tends to save us from that. But we're only about 94 million miles away from our star. So good for us. And our star is more towards the yellow, the G-type stars, versus the more energetic and unstable red and orange dwarf stars. Our sun does not spew high flux CMEs and doesn't spew them as often. But these extrastellar ones, we can observe those not visually, not in high energy, but in very low radio frequency. So low frequency radio astronomy. The particular instrument that we'll talk about is something called LOFAR. It's a low frequency array of radio telescopes. It's Earth surface based. The type of burst is called a type 2 CME. And the observations that they do is 166 to 120 megahertz. And I'll show you a spectrum of where that lines up. The one that they were looking at recently was an M-type star. This is a red dwarf, has funny catalog numbers there, but it's in the Tycho catalog. So if you have a good enough telescope, you can actually punch in the coordinates and it'll take you to that part of the sky. It's in the constellation Eridanus. It's about 133 light years away, but it's too dim and infrared, because it's a red dwarf, to be seen naked eye or even with a small scope. So how do we see these? Well, it's low frequency, long wavelength. You don't need a fancy radio telescope with a big dish to do this. You can observe them from the Earth, and we'll explain why you can do that without needing to be out in space or the far side of the moon or anything. And if you have just a single, simple dipole antenna, that's basically an antenna sticking up with a ground mesh plane beneath it, that's the receiving antenna for low frequency. You don't need a giant steerable parabolic dish. But if you have a lot of these, you can synthesize them into a very large telescope. So LOFAR is the low frequency array. It has multiple antenna types in different collections, and it, via software and electronics, synthesizes a very large radio telescope. It originally started out just in the Netherlands in 2010, but now it's in 7 different countries throughout Europe. They basically have 2 kinds of antennas. They have a 10 through 80 megahertz and a 120 through 240 megahertz. The wavelength goes from 30 meters down to 1.2 meters. This is not microwave. This is not high energy into the infrared. This is very much low frequency. The antennas are fixed. The Earth rotates, the antenna points skyward, and the object drifts across its field of view. So it makes it inexpensive to do this. The initial set of antennas were all directly coupled. They were all digitally coupled together, analog style, so they could tune the receiving offset for the individual antennas. So collectively, they would all be in perfect time sync. But as they branched out across countries, it is impractical to have a wide area network that runs high speed enough to synchronize all of that. So they had to find a different way. And the different way was they went digital. They started recording the received radio data and then time stamping it with very high resolution, very precise clocks. And that allowed them to create a synthetic aperture radio antenna that's about 1,000 kilometers in diameter and has a surface area of over 300 kilometers. And they're all just individual little pointing antennas or little flat plate antennas. The picture on the lower left is just the array. That's the analog coupled array in the Netherlands. The one on the right is one of the many thousands of antennas that they have across the entire array. In the electromagnetic spectrum, what is the low frequency we're talking about here? So the uncolored strip there down towards the left center, that's the entire electromagnetic spectrum from gamma rays to X-rays to ultraviolet to visible, infrared, microwaves, radio TV, and then the very long waves. LOFAR is that little red dotted out area. It goes from about the top end of VHF TV signals down below VHF, down below the FM band, just above the AM radio band. So it's from 10 megahertz to 240 megahertz. So that's where LOFAR can hear. Now, why is it significant that it can hear in that range? This picture shows you what radio frequencies penetrate the water vapor, gases, and the electromagnetic shield of the ionosphere of the Earth. So the brown areas are blocking radio frequency. Where the brown areas have gaps is radio frequencies that can get down further. And even light, because you can see light makes it almost all the way down. And you can see that the curve at the bottom allows certain wavelengths through. So from like kind of purple up through maybe not quite deep red, those will make it pretty well unaffected all the way down to the ground. But when you get into the ultraviolet, that starts to get blocked by the water vapor in the atmosphere. And when you get down towards the deeper infrared, that also gets blocked by the atmosphere. But if you go over to the right, you can see as the radio frequency gets lower and the wavelength gets longer, LOFAR is in there and has complete unobstructed range. So that's why LOFAR is at that particular radio frequency ranges. It doesn't get blocked. You can build big arrays of radio antennas on the ground and the signal will make it through. So what are these red dwarf and orange dwarf stars and how that compares to the sun? And this is something called a Hertzsprung-Russell diagram. This shows you the different star types and the population densities of them and their energy levels and temperature levels. So if you look across the top, you see these letters, O, B, A, F, G, K, M. There's actually a couple of more beyond there that are special case. But M are the red dwarfs. K are orange dwarfs. G is what our sun is actually a G2. So it's not precisely on G. It's a little beyond G. It's a G2. And that's where I have sun. Sun is one of those little dots in there. But the largest population of stars in the Milky Way is red dwarfs, M-type stars. There's about 75% of the stars that we've cataloged in the Milky Way that are M-type stars. They're red dwarfs. The next higher population category is orange dwarfs. They make up about 12%. The rest of them are higher energy, higher temperature, but there's far fewer of them. So if we're looking for something that has CMEs all the time, red dwarfs are the most unstable, energetic. They spit out a lot of CMEs, a lot of big ones. Orange ones are a little more stable, a little less energetic. And then when you get up to the G level to where our sun is, they're pretty quiet. How do you line all this stuff up? Well, LOFAR being fixed to the surface of the Earth and not being able to train its antennas because they're all just pointing up. If you want to observe something, the Earth has to rotate where the thing you want to observe in space passes underneath the antennas at the fixed locations on the Earth. So having multiple of them over the surface of the Earth helps with seeing more things. But still, it has to pass underneath. CMEs typically don't last that long. They may take a while for like the plasma to make it to a nearby planet, like to the Earth, takes days. But out in space, the actual high energy radio emitting part of it could be an hour or less. If the Earth is rotating through and the CME lasts beyond the direct line of sight, then the Earth will rotate out of range of the CME. So you've got a sweet spot overhead of what you can see. But since red dwarf stars have lots of CMEs and they put out a lot of photon flux in radio, even though they're still light years away, the signal's weak, the particular wavelength that you're looking for and the high flux level of it, lots of photons, it makes it easier to see it in radio because the signal to noise ratio, or SNR, is fairly high. But you need to know what frequency to look at. As a star is rotating, if the CME comes out at an off angle and kind of sweeps around, you actually get a Doppler shift in the frequency, the wavelength of the radio emission. So if you can catch a CME that's kind of pointing directly at the observatory or is 90 degrees to it, then you know what frequency you're going to be looking at because it's excited star material. This particular CME that they observed is in the 166 to 120 megahertz range, and we have relative velocity on it. But it was fairly short in duration, but they occur often, high flux, easy to spot, and they're transparent to the Earth's atmosphere, so they're easier to see. Well, we need to know more information about the particular star and the CME, so we look to the high energy level because stars are typically high energy. If we were to just look at the star visually in optical astronomy, the CME is so tiny compared to the brightness of the entire star that you won't be able to spot it. The brightness of the star will wash it out and you won't be able to see this little spike coming out of the star. So you look at it in different wavelengths. Low frequencies best because you can catch that as it leaves the star and the star's own emissions won't get in the way. Stars do put out radio emissions at a different frequency, but once the plasma leaves the star, it's on a different scale, different frequency range. So it's easier to separate that way. So what they did was they looked at this particular star in X-rays. Historically, they can look back at their observations and see, okay, that's when radio detected the CME. What did X-ray detect? And they can, from that, detect the rotation of the star, the energy level of the emission, and identify more characteristics that allow them to corroborate the CME with the X-ray observations. But as I previously mentioned, our X-ray space telescopes are running out of time. The XMM-Newton, which is the European Space Agency's X-ray telescope over in Europe, they've got maybe one more year on that before the EU shuts it down, and they won't be launching a replacement until at the earliest 2028. In the US, NASA wants to shut down its Chandra X-ray space telescope this year. It's a budget shared funding kind of thing, even though the technology and the operational status of Chandra should say it's got about another 10 years of life before it's going to run out of steam. But it's still actively returning science, but it's getting old. You know, it's more than 10 years old. So it's time for something new. There are two new X-ray telescopes already in space. One's called NuSTAR and one's called IXPE. They're both X-ray space telescopes, but they're meant for looking at different things. Chandra and Newton are very similar in the kinds of X-ray emissions that they can align with, how broad the frequency is, how sensitive the receivers are. NuSTAR and IXPE are looking for very specific X-ray emissions, but Chandra and XMM-Newton are general X-ray emissions. We'll lose an instrument that will help us with CME observations in low-frequency radio if we can't have a general-purpose X-ray space telescope. You know, LOFAR is good, but what if you could have a lot more antenna kind of LOFAR? Well, given the low frequency and given that the Earth's atmosphere doesn't deter the signal, why not use inexpensive software-defined radios to receive the signal? Confirm that amateurs can receive it, put a low noise amplifier on the front end of it, which is fairly cheap, and then record some data. And then compare that data to what the professional observatories get and see if they're similar. And if they're similar, then work on getting the cost down to the point where you can have hundreds to maybe a small number of thousand of amateur low-frequency radio observatories all observing the same sort of stuff at the same time. And if you remember how I said LOFAR started out as analog synchronized or correlated data, and then they went to digital because it just got to be too big and the wide area networking couldn't cope. On day one, have this same problem if you wanted very widely separated amateur radio astronomy going on. They would always need to be synchronized digitally. There's two sources of doing this. There's something called a rubidium clock. This is where you take essentially radioactive emissions from a rubidium source and you count those as clock pulses. And you can use that to generate a frequency that you can use to drive your receiver. And you can also use that as a nanosecond scale time source to say when you actually receive those samples. And then if you've got the deep pockets, what you really want is a hydrogen maser. And a hydrogen maser is the kind of thing that the professionals use. They're very expensive, although it's my understanding that you can get some used Russian hydrogen masers from observatories that are no longer capable of operating. And if you can get one of those and you have the money to retrofit it, those are good time and frequency sources. And Sarah in the Society of Amateur Radio Astronomers, there is an observatory over in Europe that actually makes use of a hydrogen maser, and they got it used on the cheap and then spent a lot of money retrofitting it to be the clock source and the time source for their observatory. Once you can store the data on, maybe terabyte scale storage, which is relatively cheap nowadays, you can then maybe send that data. You'd probably postal delivery ship solid state hard drive. That's the fastest way to transfer terabytes over the internet. It's just, what's the highest speed data transfer? That's a pickup truck loaded with terabyte solid state disks, not actually a live internet connection. So you could transfer that data to a supercomputing center that they already have the algorithms running to do this. So you would have to produce your data in a format that they already recognize. Luckily, there is one. The U.S. National Radio Astronomy Observatory has one called CASA, Common Astronomy Software Applications. They have a format that you can store the data in, that they have processing that will readily process that, even for LOFAR. But you need to have them allow amateurs to submit data. They can maybe have some software up front that will say, that data is good, or that's crap data, to not have to be burdened by manually analyzing less than high quality data. Once we have that and the amateurs are into it, we can have a very large diameter interferometer in North America, going from the East Coast to the West Coast, much larger than LOFAR would be. But that won't make up for the loss of not having X-ray space telescopes to corroborate the data. So in summary, we already have space-based and Earth-based observatories for looking at our sun. We're looking at coronal mass ejections of our sun. We also have them in space for looking at CMEs that occur on the backside of the sun. So if you can think of it as the Earth is on this side of the sun, there's the sun, and then on the backside of the sun, you've got another observatory that's observing that side of the sun, because it's CMEs that are on the backside of the sun that actually make their way to Earth, because the CME has kind of a rotational velocity in it, courtesy of the sun's rotation, and that's the one that sweeps around over to the Earth. If you see a CME that's directly on the surface of the sun, that's not going to make it to Earth. If you see it on the right-hand side, so the side rotating towards you, that's not going to make it to Earth. The probability goes up on the left side as it's swinging around, but the ones that actually make it to Earth are the ones on the center of the backside. LOFAR is a means of observing these extrastellar, or in other star systems in the Milky Way, coronal mass ejections using low frequency, long wavelength radio astronomy. And because the interferometer, the multiple antennas, are so far apart, they have to do high accuracy digital correlation of the data. They can't connect the links and make them work together in fractions of a nanosecond. They have to be time-stamped to fractions of a nanosecond. Observing them using something that's in a fixed location like LOFAR means the Earth has to rotate and sweep under the object. But if you've got amateurs with movable radio antennas, they can point at anything and everybody can track the same thing at the same time, regardless of where the Earth is rotating, as long as it's facing the same side. Obviously, somebody on the other side of the Earth, if you have a target there, you can't see it. Now, luckily, red dwarf stars are plentiful. They're higher output, CMEs, occurring lots of times. Unlike our sun, which is quiet, a particular wavelength does pass through the Earth's atmosphere, more likely to be observed, and we can observe them. A large-scale amateur array would be a very nice thing to have. We need cheaper, improved clock sources and time sources. We need a way of getting the high bandwidth data to data processing centers. We need a way to get amateur data where it can be contributed for professional post-processing. And then, we still need space-based X-ray telescopes for that additional corroboration. And then if you didn't know what a CME is, and then this particular CME, there was lots of articles associated with it, lots of papers, different periodicals. And then if you didn't know what LOFAR is, or what an interferometer is, the EM spectrum and why we can receive certain things at the ground level, what a red dwarf star is, that Hertzsprung-Russell diagram, and then if you wanted to look at and compare XMM-Newton versus Chandra, there's that. And then if you've got the bucks or you want to know what a hydrogen maser is, maser sounds like laser. Yes, they're both based upon emissions for stimulating radiation. Radiation is photons. Lasers do it in light wavelengths, and masers do it in microwave radio wavelengths. And then a GPS Disciplined Oscillator. This is where you have a rubidium oscillator that for time of day, it needs a base source because the rubidium is just like tick, 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 tick at a very high accuracy. But that doesn't tell you time of day. So you use the GPS to discipline or synchronize with the actual time of day. And then what a rubidium time frequency source is. So who knew you could observe CMEs using amateur radio telescopes? Comments, questions?
Did not know that.
Okay. Remember, nobody's born knowing all this stuff. They keep adding to it and changing it all the time. But as I like to say, you never know how much you didn't know until you know what you didn't know. The email address is always open. If there's any topic that you'd like for me to cover or something that you see that you want me to do a deeper dive on, just even as a news article, always available for that. Anything else before I stop recording? Hearing nothing.